Hello everyone. This is to explain how to run the MTL QSAR code that comes with the multitasking learning with a natural metric for quantitative structure activity relationship learning paper. As you can see, I'm on the GitHub repository here. So when you're there, when you open this repository, you will find some explanation that we provide here. We will make sure this is kept up to date as time progresses. But to be able to run the code, we'd like you to do two things. So download the Java source code inside this folder here. It's an Eclipse project, so make sure you import into Eclipse. And then download the full data sets that are available under this Google Drive. The reason we didn't include all the data sets here is because of space restrictions. But when you visit that link, you should be able to find the fingerprints from Campbell 20 and then the data set levels and categorization and hierarchy as we explained in the paper. So when you download everything, your project should look like this. Under Campbell 20, you should have levels 4, 5, and 6 with all the families under them. We only here have one family because just an example and because of space restrictions. So under each family, for example, the levels 4, 5, or 6, so under the preferred name groupings, each family should have a text file name. Okay, that file name, the name is the family name or the group name. Inside that file, you will find dataset names. The dataset name is the actual drug target ID or the organism ID that falls under that category, and its name corresponds to the fingerprint dataset that comes with it. So the fingerprint dataset basically will have a list of all the compounds with known activity against that drug target, and the features are fingerprints. Okay, so under this family, we have these 4 drug targets. These are the target IDs. Now, the other 2 files are the sequences that were used to compute the pairwise similarity between these drug targets, and this PID file has the similarity values, pairwise similarity values used in the similarity-based multitask learning as explained in the paper. One thing to add here is we have used Weka 3.7, so make sure you add it to your class path. Quite easy to do, just right click, you can go to properties, Java build path, and then add external jars, and you add it here. As you can see, I have it here, 3.7.13. Other than that, you just need to run the code. So let me close this and then start explaining how to run the actual code. Good, so assuming you've downloaded all the data sets, and you have under Campbell 20, you have the levels in the hierarchy, levels 4, 5, and 6, and you have also the preferred name groupings, and then here you have the full data sets with all their fingerprints, so should be more than 1,000. And then to be able to run the code, so you can go to source, MTL package, and then standard random forest is where we visit all the families, loop through all the families here under the level we specify. And please notice in the on the GitHub repository, the code we added is run on Windows, so just make sure you basically take care of the classes of the slashes. I'm sorry, change them accordingly. I'm running the code here on Mac, so it's a different separator basically. So what you do is you go to random forest, and what it will do is it'll list all the text files inside the working directory you provide, so level 5, and then it will loop through those text files, and from inside each text file it will loop through all the drug targets here, so it'll take the list drug target name, and then it will go and find its corresponding fingerprint dataset inside this folder, and then on that dataset it will run random forest with 100 trees. It will do or perform 10-fold cross validation. So normal standard random forest, no, not much is done here. So if you run this, it'll go through those files. You can see for that drug target under this family, perform 10-fold cross validation, and then it'll do it quickly and finish. Okay, so if you check the results now, I've told it to save the results under standard random forest. So if I go standard random forest, then these are the details after we've run 10-fold cross validation on each data set. So if I double click on this, it should give me the fold ID, the row ID, the actual value, and the predicted value. We'll leave it to you now to use your favorite tool or favorite programming language, R, Python, whatever, to compute the average RMSE across the 10 folds, okay? You have the fold ID here, so you can keep track of everything you want to do, okay? So that's how to run standard random forest, get hold of the splits and the actual and predicted values, and then, like I said, you can compute RMSE, R squared, whatever you want for evaluation. We'll leave that to you, okay? This will happen to each drug target under each family. Now, when we come to the MTL work, this is where we concatenate data sets and then add an extra column to specify the target ID, as we explained in the paper. Again, if we run this, it will go through the families under the path we specify. So under level 5, it'll open up this family. It will concatenate all these data sets into one big data set and then add the drug target IDs as a new column. And it will run a 10-fold cross-validation using random forest with 100 trees. And there's a key idea here, which is stratification. So in the splits we make, under the 10 splits for the cross-validation, we make sure the splits are stratified, and the stratification is based on the target ID. So we make sure that in each split we have a similar percentage of different target IDs or different instances coming from the data sets that belong to different target IDs. I hope the idea is clear here. It's explained in detail in the paper. So if we run this now, it'll take a bit of time. So it finishes concatenation, and then it does the 10-fold cross-validation. Remember now, it's using all the data under that group. Fold 9, fold 10 is finished. So if I check the results, I've told it to save the results under under results, MTL, and it'll use the group name, so we can specify it. If I go to results, MTL, group name, if I open this, you will see here that we keep track of all the folds, all the splits, and the organism or target ID. Okay, so you notice you have fold number, organism TID number, and you notice under each fold, if I go to fold 2, you notice you have different target IDs, because we're trying to learn now for each target, but within the group, so we're multitasking, we're learning several tasks at the same time, and then the row ID, the actual value, and the predicted value. Now, the beauty of this is as follows. You need to filter by drug target ID or by the organism ID. That will give you the details of the 10 folds for that particular target ID, and then you can compute your favorite metric, RMSE or R squared, and then compare it to the result you got for the random forest. Okay, so we learn the drug targets together, but when we evaluate, we look at the evaluation of each particular drug target on its own, right? I hope the idea is clear here. We need to filter by drug target ID, by organism TID, and then compute our favorite metric, as we mentioned before. So that's how we do how we run the multitask learning code, and then you get the detailed results as you can see here. A similar idea is for the similarity-based multitask learning. So this PID sim MTL file, it does exactly the same process, but now it incorporates the similarity values of the drug targets as we explained in the paper, and then it runs 10-fold cross-validation stratified based on the organism TID. If I run the same thing here, if I run this similarity-based MTL, it'll concatenate the data sets and then perform 10-fold cross-validation. A bit slower than MTL because we have more features now, the similarity values. And then I've told it to save the results to results PID sim MTL, and then just use PID sim MTL and then the group name. So if I go results PID sim MTL, open this file, it should give me similar details, fold number, the TID, again stratified based on it, the row ID. Notice the row ID the same chemical compound can exist in basically the data set that belongs to more than drug target. That's fine, but we distinguish here by incorporating the organism TID, so no problem there. Again, if we want, for example, the RMSE or R squared for this particular drug target, then we need to filter this data by that organism TID, and then we'll get the tenfolds for that particular organism TID, perform or compute RMSE or R squared, and then compare to MTL and compare to random forest results. Okay, so that's how to run the standard random forest, the MTL and the similarity-based MTL or multitask learning. In the manuscript, we explain that we run Y randomization. The idea here is that if we randomize the value or the variable which we're trying to predict, which is the activity value, if we permute it and randomize it and then try to learn, our approach should not work. So it should work with the original values, but it should perform really poorly if we randomize the class variable, okay, or the variable we're trying to predict. And this is what we do in perm MTL, so permutation MTL. We perform exactly the same stuff as MTL here, but we perform it several times, and each time we randomize or permute the class or the target variable or the activity we're trying to predict. So this is where we do the randomization here. I've done it only for 5 times here, but you can do it for 100 or 1,000 times. In the paper we say we've run it for 1,000 times. And the idea here is as follows. For each of the 1,000 times we run this stuff, we compute RMSE, for example, for the drug targets, and then compare that to the random forest or the MTL or similarity MTL we've done before. It should not work. So this randomization here should perform poorer than standard random forest, poorer than MTL, and poorer than sim-MTL. Well, if it's poorer than if it's poorer than random forest, then it should be poorer than MTL and sim-MTL, because when we do the evaluation, compute RMSE and R squared, we actually end up concluding that MTL and sim-MTL improve results and perform better than standard random forest. Okay, so enough talking, let's run this just for 5 times, and then I've told it to save the results to results rand MTL, and then it will just give it again a name according to the group name, and then the iteration number, so first time, second time, third time, and so on and so forth. And notice each time we permute and shuffle basically the class values, okay? Shuffle or randomize the class values. Let's run this. So it'll do the concatenation, and then it will start randomizing and performing cross-validation. So that's the first time. Put this up a bit. That's the first time. Finishes. Now second time, permute the class variable and do cross-validation. Let me stop here and then come back when it finishes. Okay, very good. I've paused the video until it has done the 5 time randomizations, and the results should be saved here. So I go under the family, create this folder for that family, and now each CSV file contains the results for that randomization, first time, second time, third time, fourth time, and so on and so forth. And these results will look very similar or exactly the same as the MTL results, but the values should be different. And like we said before, just open the file to view the results, filter by the organism ID, and then compute RMSE or R squared for that particular TID, organism TID, and then compare the results maybe to standard random forest or MTL or sim-MTL. Again, just to repeat and make sure we're all on the same page, it should be poorer here, and that actually gives extra credit and justification to our approach, where we show that MTL and then incorporating the similarity values actually improves learning and provides better results. Okay, so I'm gonna stop here. Thanks for watching, and let me know your feedback maybe by commenting here, under this video on YouTube, or by leaving a comment or reporting something on GitHub. Thanks again. Thank you.